Let's start with our demotivational poster. Today is the first day of the rest of your life, but so is yesterday, and look how that turned out. So now we're going to talk about linear motion elements. Linear motion elements commonly involve converting rotary motion into linear motion. And the linear motion quite often acts sort of like a gearbox does, where it has to increase the effective, well, not torque, because technically it's not torque but force. So it has to convert torque into force, and usually has to do so to generate a decent amount of force. A lot of times you're moving heavy loads with these linear motion machines, and so the motor has to trade off speed for force, essentially. You'll notice this particular design here. There's a figure on the right with the motor mounted. There's a right angle drive there. And there's also a cutaway of a very similar device on the left, where the motor would drive the worm that's on the shaft there, and then you notice the worm gear that wraps around the threaded section, the threaded rod section. And so there's a tremendous reduction in speed. Of course, that looks like it's about a 4-start worm. But there's a tremendous reduction in speed still from the worm to the worm gear, and so there's a corresponding increase in torque and therefore force in order to drive this screw thread, which is what is properly called, up or down in that fixture. There are many types of linear motion elements, of course. One type is power screws, and the square-threaded and acme-threaded and buttress-threaded screws all fall into the category of power screws. There are also ball screws. Ball screws are a type kind of like bearings. We'll talk about those. There are jacks. Jacks are typically more of a linkage, more of a complicated lever type of machine. Fluid power cylinders, if you think of hydraulic cylinders, they're typically linear actuators. Of course, air or pneumatically powered cylinders are also typically linear items, although of course you can get air motors and you can get hydraulic motors and so forth. There are plain linear actuators, there's rack and pinion gears, there's also linear motors themselves. I have an experience with linear motors. You probably have never seen these, but these devices up in the top, they almost look like a floppy disk, if you know what that was. These were called zip drives, and the first zip drives held a whole 100 megabytes. It was amazing at the time. This was back in the mid-90s or so when these things were released. Several different versions compatible with Macintosh and IBM compatibles. Several different versions, and it was just amazing to have 100 megabytes on one storage medium. Now today, of course, that's laughable because we can get thumb drives in the 64 gigabyte range or so now, and so 100 megabytes is nothing. But while I was in college, I had one of these drives, and I had some of the disks, and I would store my work on these disks. They were sort of like floppy disks, but they were a little thicker and they were a little bigger. And what was interesting about them is there was a phenomenon known as the click of death, and it was kind of interesting. The way the disk was laid out, there was enough information that you needed to keep track of kind of where everything was in the various sectors. So if you wanted to access one file, it might not all be just in one row, kind of like you would think of a record groove. It didn't work that way. You'd have to go to this sector, then that sector, then this other sector, and read the data, put it all together, and there's your file. Of course, the system took care of all that. The reason I bring this up is that the head mechanism on this device was really interesting. If you look on the right, you'll see a picture of it when the drive is disassembled. It's actually a linear motor. So it doesn't have any gearing, it doesn't have anything. I'm not sure, it must have had feedback of some type, but I'm not aware of what it was. Anyway, in keeping track of all that data and which sectors they were on, that requires what's called a file allocation table. And if you've ever seen FAT or FAT32, or NTFS, you've been dealing with a hard drive format. Well, these had their own, I believe, custom format. And what was interesting about it was it had 4 copies of it. They were called Z-tracks, and they were near the center of the physical diskette itself. And what the head would have to do is go to those tracks, read off to figure out where all of the pieces of the file were located, and then go read all of those pieces off of the physical drive itself. And what would happen is if it had trouble reading anything, the motor would literally take that whole head assembly and just slam it. I don't know if it went forward or backward, but it would just slam it, And I guess the idea was to knock off dust or something. I don't know what the idea was. I've posted a video where you can watch the mechanism moving back and forth, and that's not the slamming motion I'm talking about. The video I posted just has the head sliding back and forth, and the idea was to, I guess, to equalize wear over the whole surface of the disc. Anyway, there was a head on the top and a head on the bottom, both for reading the magnetically stored information on the upper and lower side of the disc. And if it couldn't read a Z-track, which was pretty common because the Z-tracks were overwritten so frequently because you're always changing files, and so where each piece of each file is located is constantly moving around on those Z-tracks. Well, eventually all four of the Z-tracks would wear out, and so the heads would go to the Z-tracks, try to read, and slam, and it would click. It made this clicking noise. And it became known as the click of death. The reason for that is that, of course, slamming fragile heads against a stop is not a good idea. And so what would happen is the heads would loosen up, and it became kind of like a mechanical virus. It was really interesting because the heads would, I guess, loosen up or come off, and they would damage the surface of the disk itself. And so as a user, unknowing what's going on, you'd push the little button, you can see it there, that gray button. The disk would come out, and you'd put it in another drive if you were in a computer lab to try and get your data, right, to try and read it. Well, because the surface of the diskette was damaged, that could damage the heads on that drive, and so the cycle continued. So you could destroy 10, 20 drives pretty easily, just logging into the next machine and hoping to read your data for the report that's due in a couple of hours. So it's called the click of death, and it was kind of like a hardware virus. There were all kinds of interesting interesting pop culture jokes about this. What do you do when there's something that's a tragedy, at least in your world, when you've lost all your data, except joke about it? There were some fixes, but by and large, if you got the click of death, that was it. You were done. Of course, these went by the wayside pretty quickly. They did, interestingly enough, make a couple of other sizes. They had a 250 and a 750 megabyte size that I was aware of. They even had what was called the Jazz drive, which had, I believe, more hard drive-like platters inside of it, and it held a whole gigabyte, which was amazing at the time. So anyway, linear motion elements. Let's talk about square power screws, and they're called square power screws because of the thread form itself. And so you'll see the pitch there, the distance between adjacent threads on the same helix, and that the standard size, as far as the width and the depth goes, is half of the pitch. So very simple thread. If you think about these threads and you think about taking one thread and unrolling it off of the round threaded shaft, you realize what you really have is an inclined plane. And it's really important to think about the forces acting. Now, of course, there are other threads usually engaging with the power screw threads. And the threads on the nut we could look at as a box sitting on this inclined plane, where if the box wants to fall, essentially, or if there's a load to drive that nut against, then effectively that's like a force. Okay, so you'll see the force labeled F there on the left-hand figure. That is the load to be moved by the power screw. And as the power screw turns, of course, it pushes against that load. So the object, or the nuts, that are engaged with the power screw thread actually go in the opposite direction to F. They advance upward. Now, several things are listed here, and you should recognize these from previous lectures, but the lead is the distance along the shaft that's moved with one shaft rotation. So how far, if you had a nut mounted on the power shaft, how far that nut would advance if you turn the lead screw by one revolution. The lead angle is called lambda, and you can see that listed there in the figure, as well as the effective perimeter of the screw at the pitch point. So the pitch diameter is d sub p, and then pi, of course, takes into account the fact that we're trying to calculate a circular perimeter based on the diameter of that circle. So if you think about the forces that are acting here, there will be a normal force from the power screw threads onto the nut, or we can look at that as a box. And of course there will be friction that is acting against motion, because understand the way that the box is moving is essentially up the incline. It's being pushed against the direction that it wants to go. And so since friction always acts against the direction of motion, friction is trying to prevent the nut from advancing on the power screw. If we consider then what happens when the load is allowed to move in the direction it wants to move. So imagine that you have a nut on a power screw and you're turning in the direction that the nut wants to go. Say that gravity is pulling down on the load or whatever. Well, then in that case, the amount of force required to move the load P is less, and the reason for that is that the force, the load on the nut actually acts to help move the nut down the incline. Friction acts against the direction of motion again, so understand that this box is moving down the incline now. But what's interesting about this is that the load helps the nut move down, and so it doesn't take as much force to move the load down the incline. And this is analogous to how much torque it takes to turn the power screw. As a matter of fact, we can compute the amount of torque that it would require to move the nut up or against the load. So if you think about it this way, think about the nut on a screw. So just think about a regular threaded bolt. Of course, you shouldn't use screw thread for moving a load. That's not really what it's made for, but you can think of it that way for now. So think of a nut on a threaded rod, and if the nut is trying to go one way and you're forcing it to go the other by turning the threaded rod, well, then you're moving that load up or against. You're moving against the load. And so you can calculate the torque required by either one of these equations. Both will do just fine. They'll give you the exact same result. Now, capital F is the force that is applied to the nut to try and get it to move opposite the direction that it's actually moving. D sub P is again the pitch diameter of the screw. L is the lead of that screw, lambda is the lead angle, and F is the friction coefficient between the nut that's riding on the screw and the screw itself. Typically, you're talking about steel on steel, and if it's well lubricated, then about 15% or so is a good estimate for the coefficient of friction between the nut and the screw thread. Now, the two equations I have here are equations 2 and 8 in the chapter on page 586, but there is a relationship actually among the pitch diameter, the lead, and the lead angle. Of course, if you refer back to the previous slide, you'll note that this is simply a geometric relationship for an inclined plane. All we're doing is imagining that one thread is unwrapped from the lead screw and the geometry of it captured here. So you can make the substitution algebraically if you want, and you'll arrive, you can go transfer back and forth between the left and right equation. It's just a convenient form of the same thing is all it really is. Now, what if the nut is getting to move in the direction that it wants to, in the direction that the load is pulling it? So we call that the down direction, or moving with the load. Well, in that case, here are the two equations, and they look very similar to the last two, but on close inspection you'll notice they are different. In fact, the equation numbers are 4 and 9 in your text. Square-threaded screws are, of course, not the only thread form available. What's actually more common is Acme power screws. And with Acme power screws, you have a trapezoidal thread profile. It's similar in terms of the fact that the depth of the thread is half of the pitch, but now you've got an angled sidewall, and that angled sidewall does something really important. If you notice, the left threads, figure A, are square threads, and the right threads, figure B, are the Acme threads. Now, since you're going to have these threads lubricated, the true force is going to act at an angle. Now, that doesn't reduce the amount of vertical force required at all. However much force is required in the vertical direction, that's what it's going to take to get the nut to move. However, because the effective force is at an angle, there's a component of force that acts into the thread and into the body of the screw. And what this does, partially, is that it helps push the thread into the sidewall or the body of the screw, and actually reduces the stress at the most vulnerable point. If you think about what's going on here, this is kind of like a cantilevered beam, and so the upper and lower points, or at the root of these threads, would be the most vulnerable points, and so that horizontal component helps push the material together and reduce the stress. To calculate the amount of torque required to move up or against a load, they've got equation 1710 in our text. The only new thing here is that now there is the thread angle, phi, which is a little different than what we had in, of course, square threads. There was no thread angle. Now you have to be careful about this. This thread angle is 14.5 degrees for American sized or English sized, but it's typically 15 degrees for metric screw thread. So there's two reasons that metric and English screw threads don't work together. One is the spacing between the teeth, and of course the size, but I said teeth, I meant threads, but also the thread angle itself is different. This equation is still in play, it still applies. The amount of torque required to move a nut down with the load in the direction it wants to go is a slightly different form of the equation. You'll notice that some signs have been flipped around, and that's all there is to it. You just need to know what these equations are. They're in your text. This is equation 11. There are also buttress power screws. We're not going to do anything with these, but these are a trapezoidal form where one face is longer than the other, so it's almost like a mixture between maybe a screw thread or two different angle Acme threads. Although Acme threaded screws are standard at 14.5 degrees, as I said, for English. Anyway, these threads are nice because you can apply more load in one direction than the other, but their dimensions are also standardized. Now, most of these power screws are self-locking, so they can't be back-driven, and so no torque is required in order to hold the load in place. Now, if you have a steep enough lead angle, then it is possible for them to be back-driven and not be self-locking. The requirement in order to determine whether or not the thread will be self-locking is whether the friction coefficient is greater than the tangent of the lead angle. If that's the case, then it will be self-locking. So if you look at 8.5 degrees, that's where your tan of 8.5 degrees comes out to 0.15. Tan of 5.7, a more shallow lead angle, leads to 0.1 or so. And this is about what you'd want if you have really nice smooth threads that are well lubricated, because they're going to slip easier. Of course, the friction coefficient may be less. But even with a shallow lead angle, you have to avoid vibrations. Vibrations can very easily get power screw thread to back out if there's no torque to hold it in place. The efficiency of these types of screw threads are not particularly high. The theoretical torque without any friction is given there on the top of this ratio. And the torque with friction is from whichever equation you wish. Say we're talking about moving upward, that's usually when we're interested in efficiency primarily. Use either the equations for whichever thread form you have, square or Acme, and this equation here will then give you the efficiency. Now typically you'll get anywhere from 20 to 30%. So there's a lot of energy that's wasted in frictional heating and lost. Now, to overcome this, there's another type of power screw, if you will, called a ball screw. And a ball screw is interesting because it's kind of like a power screw meshed with a ball bearing. Okay, it's like putting those two machine elements together, mashing them together, and seeing what comes out. And if you look at the figure here, you can understand how this works. You've got the ball screw, which has a threaded groove in it, and you've got the ball bearings and what's called the ball nut. Now, if you notice, what happens is these balls will recirculate in the threaded section, and as they get to the end where they would be squeezed, there's actually a ball return tube where they can come back around to the very beginning of the thread. It's a very clever little device here. They're also usually fairly precise. These are interesting. The amount of torque required for these is fairly small. In fact, usually their efficiency is 90% or better. Now, these are not self-locking. I know when I first started working for Amatrol, my colleagues in the department were redesigning one of Amatrol's robots. It was called a SCARA design, S-C-A-R-A, I believe. And so basically what that meant is that it had two horizontal axes, and so it could go anywhere in a 2D plane, but to get the up and down motion, the Z-axis motion, it used a ball screw for the end effector. So it just had a ball screw for, you could use a motor to turn the ball screw and raise and lower an end effector pretty easily. I remember my coworker working with one of these, and he picked up, they were going to use a ball screw for the end effector to make it efficient. And so he picked it up by the nut and didn't think about it, and the screw very quickly just turned and fell right out, and all the balls went all over the floor. It was quite a mess. But he wasn't thinking about the fact that that these things are not self-locking, that if you pick it up by the ball nut, the ball screw will rotate on its own, and that's very different from regular power screw threads. In fact, if we assume that the efficiency is 90%, we can simplify the calculation for torque up and torque backward, or back driving it, by these two equations here, where the efficiency E in the equations have been replaced with 90%. So those equations in your text are assuming an efficiency of 90%, which is in the ballpark. It's a very reasonable number for ball screws. Now, since ball screws are kind of like bearings, they have a load-life relationship, and there's a figure in your text that shows this load-life relationship for several different nominal diameter ball screws. So you can look up the travel life in inches rather than as when we were talking about ball bearings, we talk about number of rotations under load. And you can look up the load on the y-axis, and wherever they intersect, you can select whichever ball screw is required for that particular load-life combination. It's following the similar equation to what we had before with rolling element bearings. Now, one of the important things to think about with shafting, and in particular with lead screws, is the critical speed. And so basically what happens is this is where vibrations and whirling begins about the axis of it. A lot of times these types of devices, power screws, are used on CNC machinery. Even something as simple as the 3D printers that people are building in their garages these days use typically threaded, just regular screw thread, which, as I said before, is not necessarily the best. But even a large machine from Haas or from, what are some of the other, well, there's tons of big names out there, but anyway, even those big machines use power screws. A lot of times they'll use ball screws in those machines. But if you think about it, as you move a load inside of a CNC machine, the motor will try to turn the shaft just as fast as is practical. Well, what is practical? Well, you certainly don't want the shaft to vibrate as you move a part when you're trying to machine that part down to, maybe a 1/10,000th of an inch. So if there's excessive motion of the shaft due to vibration, then that can obviously cause failures and problems with the machine. The critical speed is also called the natural frequency of the shaft. Now, we can calculate the natural speed, or the critical speed, from the equation in the text, where D is the minor diameter of the screw, Ks is the end fixity factor, and I want to explore that a little bit. You may remember when we talked in strength of materials about columns that would buckle. There's something to be said there for power screws, but hopefully you can understand that the way that the ends of the shaft are fixed will affect the natural frequency of the shaft as well as whether or not it will buckle. We'll talk about buckling in just a minute, but if you look at the first example there, the first picture at the top, this is an example where the left end of the power screw is fixed. In other words, there's two bearings there, and so there's no rotation allowed. Now, I don't mean rotation about the shaft axis. Obviously, it has to rotate about the shaft axis. But imagine grabbing the free end of that bar and pulling down on it. Well, that's, if you do that, that load would be supported because there are two bearings side by side there to prevent rotation of the opposite end. But you could certainly bend the shaft, right? Now, in that case, this end fixity factor, Ks, is 0.32 in order to calculate the natural speed. If you have what's called a simply supported power screw, then you have bearings at either end, and the assumption is that these bearings do not prevent any rotation. So imagine that this is kind of like a beam with simple supports, and you could put a load in the center, and it would flex, right? It would pivot at either end. And so that's what's going on here, and our factor, our end fixity factor, recommended there is 1. If you have one end simply supported and the other one fixed, then a factor of 1.55 is recommended. If both ends are fixed, in other words, both ends, neither end can deflect, it has to stay straight on either end, despite the loading, then a factor of 2.24 is recommended for this equation. And so L is the length between the supports, and then SF is a factor of safety. And what this equation is really doing is trying to predict a speed. And typically you're trying to find the high end speed, the upper end speed. That's typically where you have problems. And so you'll notice the safety factor brings that natural speed down to a lower speed where you begin to be concerned at a lower rotation RPM. So anyway, this is equation 1715 on page 591. Buckling is also a consideration. Now, this is something different. It does depend on the end fixity of the power screw. But here we're talking about the shaft simply buckling, not due to its rotation and hitting a natural speed, but just simply buckling due to a compressive load. Now, you can analyze this just as if it was a simple column. And so to remind you of the recommended values versus the theoretical values, I've found a chart and included it here for you. But this is the same thing as what we did in strength of materials. You're just analyzing the shaft as if it's a column. And so you just need to refer back to your Euler and Johnson equations in order to determine is it a short column, is it a long column, and go from there to determine whether or not the shaft will fail due to a compressive load. The critical factors all obviously are the length, the diameter, and as I said, the fixity at either end. There's another type of machine element you may want to be aware of. Since we talked about ball screws, we can talk about ball worms. What's interesting about this is that this is a new take on an old idea. So you notice that the red shaft has balls in it, so it's kind of like a ball screw. And the lower shaft, the blue shaft, has a gear, at least that's what it looks like on the end, but the gear teeth actually are made for the balls to interface with. And so as you turn the upper shaft, the red shaft, the blue shaft rotates, and this acts just like a worm gear set, except that it has the improved efficiency of a ball screw, and you can typically back drive these, which is pretty interesting, pretty neat. And of course the reason for this is because the ball bearings reduce the bulk of the friction down to nothing, or close enough to it.